Welcome back. You have a conic given by the polar equation r equals 10 over 5 minus 2 sine theta. Sine theta, so that tells you the directrix is parallel to x-axis. Okay? This minus tells me the directrix is below the x-axis. So, as always, you want to get a 1 over here. So, get a 5 out. 5 divides in 10 2 times. This quantity is your eccentricity, which is less than 1. Moreover, E times D is the numerator. It should be 2. Yeah. E times D is 2. That tells you D is 5. Okay. So when the directrix is y is negative d, eccentricity is less than 1, you get an ellipse. Directrix for the given conic is negative y equals negative 5. Major axis is on the y-axis. You get the when you get major axis is on the y-axis, you want to find vertices. You obtain vertices when theta is pi over 2 and theta is 3 pi over 2. When theta is pi over 2, you get r equals 10 over 3. Theta is 3 pi over 2, r equals 10 over 7. So you have these 2 points in the rectangular coordinates. The minor vertices are the x-intercepts, theta equals 0, theta equals pi over 2. Both cases you get 2 and negative 2. So this is incorrect, it's positive 10 over 7. That's your ellipse. Okay, this is r is 10 over 7, that should be positive 10 over 7. This is a positive. So it's on the negative side because we are using rectangular coordinates here. All right. So these are the rectangular coordinates. So it's fine. R is 10 over 7. So anyhow, so this is your ellipse. So this entire material closely follows textbook by James Stewart. What is the polar equation of the conic rotated by pi over 2 radians? So this is your initial curve. You want to rotate this by pi over 2. In other words, theta is replaced by theta minus pi over 2. Sine of theta minus pi over 2, you can expand it. Difference angle formula, sine theta cosine negative pi over 2 plus cosine theta sine of negative pi over 2. Cosine of pi over 2 negative pi over 2 is 0. Sine of negative pi over 2 is negative 1. So that becomes a negative. With a negative out here, you get 5 plus 2 cosine theta. So that's the polar equation. These polar equations of conics have very important use. Much has been studied. Here is, for instance, Kepler's laws of planetary motion. A planet revolves around the sun in an elliptical orbit with the sun at one focus. The line joining the sun to a planet sweeps out equal areas in equal times. The square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit. So, square of the period of revolution of a planet. Okay. With all of this, the polar equation of an ellipse with focus at the origin, semi-major axis A, eccentricity E, Directrix x equals d can be written in this form. If you are given semi-major axis A, eccentricity E, directrix d, you can write the polar equation of the ellipse. Now, why do we need this? The position of a planet that is closest to the sun is called perihelion. Distance is called perihelion distance. The position of a planet that is farthest from the sun is called aphelion. This distance is called aphelion distance. So sun is somewhere here. Perihelion is the position of the planet closest to the sun. And the farthest distance is called aphelion. So your planet is going around the sun. How do you obtain perihelion distance? Well, that's right here. So theta is 0. How do you find aphelion distance? That's over here. Theta is pi. All right. So this completes lesson 10.6. We will continue our next course in our next videos.